Well, thanks for joining us today. Today I am going to talk about how to push your instruments past their specifications. And this is a topic that I am always really excited about because I love playing with instrumentation and finding ways to push them to their limits and get the best results out of the instrumentation. First, I want to start out by defining water potential and going over a quick overview of what was discussed in Water Potential 101 and 201. And water potential is defined as the energy required per quantity of water to transport an infinitesimal quantity of water from the sample to a reference pool of pure free water. And an easier way to look at this is that in soils, water potential essentially is the energy required, for example, for a plant to pull water out of the soil. And water potential has a lot of applications in soils, and it's an important tool and an important property to understand in soils. Some important points about water potential. Water potential is a differential property, so a reference must be specified. And in soils, we use pure free water at the soil surface as a reference. And at this point, its water potential would be 0. And as the soil dries, we tend to get negative values from that point. The water potential in the environment is almost always less than 0 or a negative value when discussing this is in terms of water potential. Now, this would be different, for example, in saturated conditions or ponded conditions, but typically in the environment, this is almost always less than 0. Water in tissue or soil is very different from water in a glass. In soil, we're dealing with water bound to surfaces, diluted by solutes, under pressure or tension. It's a very different energy state from free water, and that really provides issues when trying to measure water and understand water as it moves through soil and how it can be uptaken by plants. Some other important points. One thing to understand is there are several names for the same measurement. So typically when we talk about water potential, we're talking in terms of negative units. Other terms that are used are water tension, soil suction, and soil pore water pressure. These are the same measure, but typically when we talk about these, it's actually the opposite value. So for example, if we're talking about a water potential at negative 33 kPa, if we were talking about this in terms of soil suction or water tension, it'd be positive 33 kPa. But we're essentially talking about the same thing, we just, it's displayed differently. And typically when we're talking about water potential in soils, we typically use units of pressure, for example, megapascals, kilopascals, meters of water, or bars. It can also be talked in an energy state, for example, joules per kilogram. But typically, most people use most likely kilopascals or bars. Those are some pretty common terms. Water potential is influenced mostly by these 4 things. One is the binding of water to a surface. So in this case, it's going to be a binding of water to the soil particles and other particles such as organic matter within the soil. Also, the position of water in a gravitational field. So for example, in this image that we have here of a soil profile, if we were using the surface as our reference, the deeper we go in the soil profile, we have a gravitational potential that we would have to overcome. So for example, if we were down negative 70 centimeters within the profile, we would have to overcome that gravitational potential. It's also affected by solutes in water. So salt increases affect the water potential. And then the last thing that we typically refer to is the pressure on the water, so hydrostatic or pneumatic. This is typically going to be when you have ponded conditions or saturated conditions where you actually have a level of water above your reference point or above your point that you're measuring at. Now, when we talk about total water potential, it's essentially a sum of those four components that we just talked about. So we have psi t, which is our total water potential, which is a function of psi m, which is our matrix potential, which is those adsorption to the surfaces. Gravitational potential, which is again based on the position relative in a gravitational field, so psi g. Psi o is the osmotic potential, or it's the effect of solutes on the water potential. And then psi p, which is the pressure potential. And all of those components combined make up the total water potential. Now, when we're trying to measure soil water potential, as far as instrumentation-wise, we have three different categories of tools that we use for measuring water potential, whether in the field or in the lab. This first method is solid equilibration methods. And within these methods, we have a few different tools. We have electrical resistance methods, which involves granular matrix, where we are inserting that granular matrix into the soil. It comes into equilibrium with the soil, and we are measuring the electrical resistance of that granular matrix. We have the capacitance method, where we essentially are inserting ceramic discs that we know the moisture characteristic curve, or the moisture properties of that ceramic, allowing it to come into equilibrium, and then measuring, using the capacitance method, measuring the water content of that ceramic, and then outputting water potential. And then last but not least, thermal conductivity method, where we again install a ceramic cup or a ceramic material into the soil, allow it to come into equilibrium, and we measure the thermal conductivity of this material, and we're able to use that measure to determine water potential. And with all three of those methods, it involves putting some sort of material into the soil, allowing it to come into equilibrium with the soil, and making some sort of measure of that material. We then have the liquid equilibration methods, which in this method, we're mostly talking about tensiometers. And what tensiometers do is we insert, for example, a ceramic disc or a ceramic cup, into the soil, and this ceramic cup is either filled with water or it has a shaft filled with water. You can see a picture of that example here. And what we're doing is allowing it to come into equilibrium with the soil, and we're measuring the pressure that, as the soil pulls the water out of the tensiometer, it's creating a suction, and we're able to measure that with, for example, a pressure transducer. And that gives us a direct measure of the matrix potential. It does not give us measures of the other components, the osmotic potential, but it can also give us a measure of the pressure potential when we do have saturated conditions. And this is probably one of the most accurate methods. The problem with the liquid equilibration method is it's limited it within range. Typically, a tensiometer, we can only measure down to negative 85 kilopascals, maybe 100 kilopascals. Except for some special tensiometers, we're able to use some special techniques to push the range of the tensiometers, and I'll talk about that a little bit later. And then last, we have the vapor equilibration methods. And within the vapor equilibration methods, we have, for example, a thermocouple psychrometer or a dew point potentiometer. And with both of these instruments, essentially what we're doing is measuring the relative humidity and using that measure of relative humidity to determine water potential. Another technique that's been used for a very long time for measuring and creating moisture characteristic curves is the pressure plate. The pressure plate was introduced in the 1930s by L.A. Richards. And essentially what we have here is an apparatus where we're inserting samples and using the pressure above the soil sample with water in a saturated sample, forcing it to come into equilibrium with the applied pressure. So for example, if we wanted to bring a sample to 10 kilopascals, we would apply a pressure of 10 kPa and let that sample come into equilibrium. And typically, we have to deal with equilibration times. For wet samples, when you're just trying to come to anywhere within the 0 to 100 kPa, you're looking at usually equilibration time of less than a day, sometimes a little bit longer. Now, when we're trying to get dry samples to come into equilibrium, anywhere between the 100 kPa and 1500 kPa, this usually takes a week or longer. And there are a lot of publications out there saying that these samples may never come into equilibrium using this technique. An example of this is in a publication by Batelli and Fleury from 2008. And so that really gives us a problem when we're working in that range of 100 to 1000 kPa, trying to develop moisture characteristic curves and get accurate measures. It really creates issues, and so we have to look at other methods for measuring the moisture characteristic curve. So just some important points on instrumentation. There really is no ideal water potential instrument to measure across the full range of the moisture characteristic curve. There are many good choices for instruments. Really, what you have to think about there is what is your goal? What range are you trying to measure within? What accuracy do you need? And what is your price range as well? But those are all things you need to think about when looking at instrumentation. And really, these techniques must be combined to get a complete understanding over the entire range of the moisture characteristic curve. Some applications of soil water potential include when we use the soil moisture characteristic curve, it gives us a great understanding of what plant available water is there. It can also be used for doing different measures such as surface area of soil, soil swelling potential. This is a common tool used especially in the geotechnical industry, where swelling potential of soils can cause issues in road construction, home construction, and other building construction. So that's a common application of using moisture characteristic curves. And really, water potential is a key component in understanding soil and plant water relations in the field. It really is the controlling factor in plants' availability to pull water and able to survive in different conditions. Water flow and contamination transport studies are also a very common application of water potential, because again, just as with plants being able to pull on water, water flow through soil is predominantly controlled by matrix potential and some other factors such as hydraulic conductivity, but they all play a role in water flow through soil. And of course, in irrigation management, knowing soil water potential is so much more powerful than water content, because again, it gives us a better understanding of the plant's availability to pull on the water in the soil. So here's a brief outline of the rest of the presentation. We just did an overview of some of the topics discussed in Water Potential 101 and 201. We'll go into an introduction into the HYPROP method, or the Schindler evaporation method for measuring water potential, an introduction into the WP4C, talk about some issues with hysteresis and sample density issues, go over some special considerations when using the HyProp, how to expand the range with the HyProp, how to fine-tune your WP4C skills, and then going into combining data from the two instruments to create the full moisture characteristic curve. So before I start talking about the instruments, I want to talk a little bit about what we used to call as this kind of no man's land of water potential instrumentation. So if you look on this chart here, you'll see we have this grayed out area in between about 150 to 200 kPa and -1 megapascal. And in the past, we really used to have issues getting good measures within this range to really fully characterize what's going on in the soil. And in many instances, this is an important range within the moisture characteristic curve. And so it was really imperative that we find a way to close that gap and find instrumentation that can help us cover the full range of the moisture characteristic curve. And in the past, with some of the older techniques, even with the dew point technique, before some recent changes, we were not able to fill that gap and get good measures within that range. But we've made some strides and have really been able to push our capabilities in making these measures, and we'll discuss that further in detail as we go through these slides. So first, I want to talk about the Schindler evaporation method. And essentially what we have when using the Schindler evaporation method, we have a device where we have two tensiometers at different points within the soil. And we are measuring the change in soil suction or the change in water potential as the soil sample naturally dries at the surface. And what this gives us is, one, a measure of the change in water potential. It also gives us a change in unsaturated hydraulic conductivity. So we're able to not only do the moisture characteristic curve, but we're also able to do an unsaturated hydraulic conductivity curve. And we'll talk a little bit about the math that goes into that here. So when running the HyProp is set up with a saturated soil sample. So before putting the sample in the HyProp, we'll fill the tensiometers, and I'll talk a little bit about the filling process of a tensiometer. And then we'll take a saturated sample and auger out 2 small holes for the tensiometers and put the sample on the HyProp. We will then set the HyProp up on a scale and connect it to a computer, and we're logging over time the change in water potential at the 2 different points within the sample and the change in weight as the sample dries down. And this allows us to get the water content change and the change in water potential of the sample to help us generate that moisture characteristic curve. Typically, this process takes about 4 to 7 days, depending on the soil texture, also depending on conditions within the room that will control the rate of evaporation. So I'll just briefly go into the calculations that the HyProp does to measure the water potential and the unsaturated hydraulic conductivity. And we won't focus too much on this. But essentially what we're doing is, again, at 2 different points within the sample, over time, we're measuring the tensions at the 2 different points and the sample weight. And so what we're able to do is we're able to take the average water content or the change in water content and the medial water tensions and give a discrete value of the retention function at any time. And it's a really amazing thing to be able to do, because we're able to generate a lot of points across the moisture characteristic curve over time, very simply with little work once the apparatus is set up. And just to reference some of where a lot of the work that goes into this technique came from, there's a good publication by Uwe Schindler and L. Mueller from 2006 titled "Simplifying the Evaporation Method for Quantifying Soil Hydraulic Properties." So if you want a good read on the evaporation method, that's a great publication to look into. So some other calculations, we are also able to calculate the unsaturated hydraulic conductivity using the Darcy-Buckingham's law. And essentially what we're doing is using the mean hydraulic gradient, or the change in tension between the 2 different tensiometers, along with a change in water content. And by using those combined factors, we're able to determine the unsaturated hydraulic conductivity throughout the drying process. Now, one limiting factor here is in wet conditions, when there's little difference between the bottom and the top tensiometer, we're not really able to determine an unsaturated hydraulic conductivity. So in some samples, especially very coarse samples, we can only generate a few points along the unsaturated hydraulic conductivity curve as the sample dries. Now, with the HyProp and with many techniques, there are assumptions that are made. One assumption is that there is quasi-steady state conditions, and essentially what that means is that the evaporation rate over the soil sample remains fairly constant over the entire process. And so that's mostly going to go back to conditions within the room staying constant. And that's an important factor, and we'll kind of discuss that a little bit more when using the HYPROP. Another assumption that's made is linear decreasing water content over the sample height within the measurement interval. And there was a lot of work done, and a lot of that work is done in that paper that I just talked about to determine if this was really a valid assumption and if that really worked well for this with technique. And what they found is that it did work, and that's why the HYPROP was made the way it was made. Okay, now we'll go into the chilled mirror dew point technique. And essentially what we're doing with the chilled mirror dew point technique, we're taking a mirror attached to a thermoelectric cooler and warming and cooling the mirror until we reach a dew point, and measuring the formation of that dew with an optical sensor. And what that gives us, by doing this with a sample that's coming to equilibrium within that chamber, we are able to determine the relative humidity of this sample. And some other measures that are made, so we use the mirror temperature when the dew is forming, and we do this continuously until we find that we've reached a steady state or an equilibrium within the sample chamber. And we're also measuring the sample temperature with an infrared thermometer. And water potential is approximately linearly related to the sample temperature minus the dew point temperature, or it's essentially the vapor deficit. And we're able to relate relative humidity to water potential by using the Kelvin equation. So by using the relative humidity and the water potential and using the Kelvin equation together, we're able to get a direct relationship of water potential. Now I bring this chart up to kind of talk about, to show changes in relative humidity at different water potential points. So I think an important one to look at is look at the relative humidity at field capacity. We have a relative humidity of 0.9998. And then the relative humidity at permanent wilting point. We have a relative humidity of 0.989. That is a very small change in relative humidity. And so it requires an accurate measurement of relative humidity to really get an accurate measure of the water potential. And in the past, we've been able to do a pretty good job of this, but we weren't really able to push ourselves up into that wet end until probably now we're able to push ourselves further up into the wet end, and I'll talk about that a little bit as I continue to talk about the WP4C. But I did want to show this because it shows that with this technique, you really need an accurate measure to really get of relative humidity to get an accurate measurement of the water potential. So with the WP4C, typically we use the WP4C as the dry range instrument, whereas when we're using the HYPROP as the wet range instrument. And we use those two instruments together to get the full moisture characteristic curve. And with the WP4C, we're able to measure water potential with an accuracy of plus or minus 0.05 megapascals. And with this, we're having to resolve temperature differences of 1/1000th of a degree. And that's a very, you're looking at very small changes there, just like I talked about with the relative humidity changes. So with these improvements, in the past we were not able to measure that accurately with this technique, but now with latest improvements, we're really able to improve the technique and push ourselves up into the negative 50 and in between the negative 50 and negative 1000 kPa range, which really is powerful when trying to combine this instrument with another instrument like the HYPROP. Okay, so now we're going to go into some hysteresis and sample density issues. Talk about some considerations when using the HYPROP and how to expand the range with the HYPROP and fine-tuning your WP4C skills. So, you know, one thing that has to be understood, hysteresis is a well-known phenomenon in soil. And the definition of hysteresis is difference in the relationship between the water content of the soil and the corresponding water potential obtained under wetting and drying processes. And below is an example of that, where we have a few different soil types that we've generated moisture characteristic curves using both the wetting and drying process. And this is a great example showing the hysteresis within that sample. And this is something that has to be considered when using any instrument and how you run the instrument to combine them together to generate the full moisture characteristic curve. And I'll show you a great example of this where we used two different techniques with the two different instruments, and it created some pretty drastic differences in the moisture characteristic curve. Another thing that has to be considered is sample density. Prior to the upgrades made to the WP4C, where we weren't quite able to get up and accurately measure up into the wet range, sample density was not much of an issue. And but as we now try and push further up into the wet end, it becomes more critical. And below is a graph that kind of shows some of the, or shows the different adsorptive forces kind of across the moisture characteristic curve. So as we're getting into the wet end, so the 100 kPa to the saturated to negative 100 kPa range, we're dealing mostly with capillary forces and the water being held by the capillary forces within the soil sample. And so in this case, soil structure, sample density are going to be very critical and going to have a major effect on the water potential. But as we get drier and get more into the absorbed film range, we're dealing more with water absorbed just the soil particles themselves. And there's been research showing that in this range, sample density doesn't play, and structure doesn't play nearly as much of a role, and so we can get away with using disturbed samples to measure within this range. But as we're trying to push into the wet range, now we're dealing with sample density issues, and this has to be considered when taking samples and trying to measure the moisture characteristic curve. So some considerations with the WP4C. First thing you want to think about, of course, is your sample collection. You need to determine whether you want to take an intact sample or use a disturbed sample. If you're not really concerned with pushing into the wet range, or if you're using a disturbed sample throughout for generating your entire moisture characteristic curve, then it's okay to use disturbed samples. But if you're using intact samples and you're trying to push into this wet range, you might want to consider taking intact samples for both instruments, say, for example, an intact sample with the HYPROP and an intact sample for the WP4C. And this is possible with the stainless steel sampling sample cups. You can go out into the field, dig a small little trench or a small hole, and lightly tap the sampling rings into the soil and take out a small intact sample. And this was something that we did for some samples that we ran, and I'll show some of the results from that later. Now, if you're going to use disturbed samples with the WP4C, what you want to do is you want to take a soil sample, put it in a cup, and add a certain amount of water. And you want to use multiple samples and add different amounts of water to each sample to get different points along the moisture characteristic curve. But what you do is add the water to this sample, mix the sample, seal it, and let it stand for 24 hours, allowing it to come into equilibrium. And then you'll take that sample and do a subsample into your sampling ring and run that on the WP4C. So some other considerations. Really, I always feel that the more samples, the better. Typically, when we're running moisture characteristic curves, we use anywhere from 10 to 15 samples. at different water contents to generate the dry end with the WP4C. And one thing that you really have to watch out for, especially if you're trying to push further up into the wet end with the instrument, is you need to run your measurements in a room with stable temperature conditions. Temperature variations due to heating or cooling can cause major issues when trying to measure in the wet range. So you really want to look out for that. And I'll show something that we use. It's going to look very crude, but something that we use to help establish more stable conditions around the WP4C. When running your samples, for dry samples, just say drier than -2 megapascals, you'll want to run, you can run the samples in precise mode or even fast mode for the very, very dry samples. And this will give you an accurate measure for that range. And as you get further into the wet end, you're going to want to run samples in continuous mode. And typically when you're doing this, it helps to have the WP4C connected to your computer. And you can use a HyperTerminal program, or you can also use the Aqualink software to watch the changes in water potential. And what you'll do is you'll just run it in continuous mode and watch for stable measurements. And so you'll be looking at the outputs from the WP4C and look for a continuous output of the same measure and of the same water potential value within a small amount. And this will give you a indicator that you've reached stable, that you've reached equilibrium within the sample temperature and you have stable conditions in there, or within the sample chamber. Now, going back to that temperature stability thing, if you are in a room that does have some minor fluxes in temperature due to air conditioner coming on and off or a heating unit coming on and off, one thing that does help, and it seems kind of crude, but it does work, is putting the WP4C in a box to help create a more stable boundary around the WP4C. And you can see an example of what we've used in the lab. And it's just a simple cardboard box where we have a piece of Velcro that allows us to open and close the box back up. And this is a great way to help create stabler conditions around the WP4C and allow you to push yourself further up into the wet end with the instrument. Now, essentially what you'll do is you'll insert the sample, seal the chamber, allow it to read. Typically, when running in precise mode, you're looking at around 5 to 10 minutes per sample for it to come to equilibrium. And as you get into the wet range and you're running it in continuous mode, you're looking at anywhere from 15 minutes up to maybe even 30 minutes on the very wet end to come into equilibrium. You'll then take that sample back out, dry it, or weigh it, dry it, and weigh it again to get your water content to correspond with that water potential point. Okay, now before we go on to talking about the HYPROP, I want to go again and talk about that no man's land. And one thing that's really helped with this, along with improving our capabilities with the WP4C, is the extended range that we're able to obtain with the HYPROP tensiometers. So like I talked about before, a typical operating range for a tensiometer is, say, 0 to -100 kPa. After that, you start getting into cavitation due to actual boiling of the water under vacuum. And so that's a really limiting factor. And what we've been able to do is we've used a special ceramic and special tensiometers on the HYPROP that with proper use and good technique, we're able to push the tensiometers even further up into the water potential range. It's possible to push the tensiometers up to -250, and I've heard some instances, and this is not something I've been able to attain, but of pushing the tensiometers all the way down up to -350 and 400 kPa, which is phenomenal. But you know, we are able to push the tensiometers further than normal, which allows us to help close that gap in the water potential range. And so this is something that we're able to do with the HYPROP to help close that gap. And so now to go into some considerations with the HYPROP. One thing that's absolutely critical with the HyProp is filling of your tensiometers. If you really want to maximize your capabilities with the HyProp, you really want to focus on a good fill of the tensiometers to really push them up into the range. We'll talk a little bit more about some things to consider there. As with the WP4C, again, you want stable conditions in the room because of the assumptions that are made in the calculations, that quasi-steady state assumption. And so it's always helpful to have a room with semi-stable conditions. It's not quite as critical as with the WP4C, but it's definitely critical. And so that's something you want to look out for. And another thing, because we're taking weight measurements, you want a stable platform for these weight measurements. You don't want a table that's going to be getting bumped into. You don't want to have a weight room right next to your lab, which was an issue that we've had before, where weights are getting dropped on the floor and actually causing the platform to shake and messing up your weight measurements. So again, a stable platform for weight measurements is very important. So now let's go back and let's talk about that extended measuring range with these tensiometers that allows us to push us a little bit further up. There are three factors that influence the extended measuring range of a tensiometer. The first factor is the bubble point. If your tensiometer has a low bubble point, then you're going to get air in there anyways once you reach a certain suction. But with the tensiometers used on the HyProp, they actually have a bubble point of 8.8 bars. So that's really not a factor there. So we're able to push, the bubble point is not going to limit what we can do with the tensiometers. Another factor is going to be the vapor pressure or the boiling point of water. Typically, depending on elevation and some other conditions, your boiling point of water under suction is going to be at room conditions, so at 20 degrees C, you will reach boiling point of water at 20 degrees, at 99.7, I believe, 99.7 kPa of suction at sea level. And of course, this changes as you change in elevation. You do get a change in your boiling point at room temperature under vacuum. And so the third factor is the ability to for boiling retardation. What allows us to do this is in order for the water to boil, it needs a nucleation site. And so the shafts on the tensiometer, on these tensiometers, the inner shafts on the tensiometers for the HyProp have a smooth surface in order to prevent any possible nucleation sites for boiling. And so we'll go and talk a little bit further about that. So in order to maintain that, we need to make sure the shafts stay clean. But here's an example of us being able to push the tensiometers further up into the measurement range. And so here's a actual measurement with one of the HyProps where we were able to push the top tensiometer up to about 1900 hectopascals, so which is 190 kilopascals, which is well beyond the typical measuring range of a tensiometer. And we were able to push the bottom tensiometer all the way up to almost 2200 hectopascals, so almost 220 kilopascals, which is a great area to reach, or something you want to try and reach with these HyProps. It is possible to push them into this range and beyond that. So keys to a good fill. Whether you're using the syringes or a vacuum system, it's important that these three things below are considered. One, you want to have well degassed water. If you don't have well degassed water, you're not going to have a good measure. And the only thing that really helps with that is time. So you just have to take your time when degassing the water, whether you're using the syringes or using the vacuum system. And again, a clean inner tensiometer shafts and clean HyProp. This really what controls this is how you finish up using the HyProp. If you don't clean the HyProp properly before removing the tensiometer shafts, you run the risk of getting soil particles or dust or other things inside of your tensiometer shafts or inside of the HyProp sensor cavities. And this will provide a nucleation site and really reduce your ability to push the tensiometers further up into the range. And then, of course, last but not least, patience. With this instrument, the only thing that helps in getting a good fill is time and taking your time. And so you want to have patience when filling the tensiometers, especially with the syringes. That takes more patience than any of the other, than using a vacuum system. But if you're patient with your fills and you take your time, you can, even using the syringes, you can push your tensiometers well beyond a normal measuring range of a tensiometer. And so one thing I wanted to go into is using a vacuum system and some things you want to consider, because this is a question I get a lot. One thing you especially need when using a vacuum is a leak-free system. So that goes into the type of line you use, the type of connectors you use, and using kind of not high quality, but you don't want to use old line or old connectors because you run the risk of having a leak. One image you can see here is to connect the tensiometer shafts to the vacuum line. I actually use a silicon rubber that's slightly smaller, has a slightly smaller inner diameter than the tensiometer shaft outer diameter, and this allows us to get a good seal around the tensiometer shafts. And then the tensiometers will be placed in a beaker with previously degassed water, and then put under vacuum, and the water is pulled in through the tensiometer shafts to fill through the outer parts of the tensiometer shafts to fill the inner part of the tensiometer. Another consideration is you do not want to use too powerful of a vacuum system. If you use too powerful of a vacuum system, you're going to blow out the tensiometers, the pressure transducers, which is something you want to avoid. So typically when we're looking at this, when you're putting the tensiometers and the HyProp system itself under vacuum, you want it to take anywhere from 20 to 30 seconds, maybe even up to 45 seconds to reach the full vacuum of your system, which is going to be about 87 to 90 kPa. Again, depending on your elevation. And what helps to protect the pressure transducers is a buffer bottle. We use a 1 liter buffer bottle. This helps protect the pressure transducers, one, from the pulsing of the vacuum system, because vacuum systems do pulse as they're pulling a vacuum, and if it has too strong of a pulse, it can damage the pressure transducers. One thing that helps for when doing this setup is having an external pressure gauge. This allows you to watch the pressure change over time, and it also allows you to know when to come back and put the system under vacuum again as you're filling the tensiometers. Another thing that might be helpful is a desiccant chamber in line to prevent damage to the pump. Because you're pulling vacuum over water and pulling on this water and essentially pulling air out of the water, you're going to have air that's close to or not at a 100% relative humidity. And this, for some types of vacuum systems, can damage them. So you might want to consider having a desiccant chamber in line. When you're doing this, typically you want to put the system under vacuum from anywhere from 12 to 24 hours to get a good fill. And so this goes back to that patience thing. So another great thing that allows us to even further extend the range of the tensiometers is we're able to use the air entry point of the ceramic to get another measurement point along the moisture characteristic curve. Because what happens when you're running a tensiometer, so you're running it through its normal range and then it cavitates. And typically when it cavitates with these tensiometers, it'll drop down to about 880, 860 hectopascals or 88 kilopascals. And then if you allow it to keep running, eventually what's going to happen is you're going to reach the air entry point of the ceramic within the soil. And with these ceramic, it's about 8.8 bars. And when that entry point is reached, you're going to see a very fast drop from 880 hectopascals all the way down to 0. And so we're able to use that point as that drop point as a reference to when the soil reached 880 kilopascals, or 8.8 bars. So that gives us another point on the moisture characteristic curve, which is really useful when combining this with instruments like the WP4C. So there is a publication on this, and seem to have lost it. It's another one by Uwe Schindler. It's titled, I can't think of it. Sorry, it pertains to pushing I think I have it actually on one of the next slides. So we'll look for that. But now we'll talk a little bit about combining data from the two instruments. Oh, sorry. Actually, this is out of place. We'll talk, now we're going to, oh yeah, okay. So now we're going to talk a little bit about combining data from the two instruments. When creating the full moisture characteristic curve, it used to be a little bit more of a pain when you're trying to model and generate fits to data from two different instruments. But with the HyProp fit software, we're able to combine data from the two instruments fairly easy with the HyProp fit software. And you can kind of see a screenshot of that below here. This allows for fitting different curve models to a data set. So for example, you wanted to combine, you wanted to generate a fit using the Van Ganukten equation, or the Van Ganukten bimodal, or Brooks and Corey, or whatever model you'd like to use and fit that to your data. You can easily add data from a variety of instruments, whether it be the WP4C or pressure plate or thermocouple psychrometer, or whatever it is that you might use. You're able to combine data from the HyProp to the WP4C within this within the same data set and generate the fits using the HyProp fit software. And so really quick, I want to show an example of some soil samples that we've run using the HyProp and the WP4C. The three samples I'm going to show you are, one is a Kiona very fine sandy loam. It's about 64.4% sand, 10% clay, and 25.6% silt. And this is data based on NRCS soil survey. The second sample was a Schwana loamy fine sand, 79.4% sand, so very high in sand, low clay content, and pretty low silt content too. And then the last sample I'm going to show you is a Palouse silt loam. Those values are out of place. I think it's about 21% sand, 67.7% silt, and 21% clay. Yeah, so that's not sure what happened there. But here's that Schwana loamy fine sand. And what we're looking at here is the triangular data points are data points generated by the HyProp. And you're looking at water content on the y-axis, volumetric water content, and water potential in kilopascals, or negative kilopascals, on the x-axis. And then we have square data points generated by the WP4C. And you can see we were able to push the WP4C all the way up into the almost field capacity point of this sample, and matching that up with the HyProp. And this allowed us to generate a very nice moisture characteristic curve, and generate a nice fit to that moisture characteristic curve using the Van Ganukten bimodal equation. So now our next soil sample is a Kiona fine sandy loam. And on this sample, we're going back to the issues with hysteresis. And so with the HYPROP, we're using drying technique. And for this sample, when we were running it on the WP4C, we used a wetting technique where we're slowly adding water to the different samples. And what that caused was us to have a little bit of a miss when measuring in between about 100 kPa and 1000 kPa. And so this shows that issue that we run into with hysteresis. And so that's something that you have to consider. And so one thing that you can do to counteract this is use, instead of a wetting technique with the WP4C samples, you can use a drying technique where you fully wet the samples and dry them down at different rates for the different samples, and then let them come into equilibrium and measure those on the WP4C. And the next example is an example where we did that. So this is a Palouse silt loam, and with the Palouse silt loam, we were able to push the samples all the way up into the wet end and match them up with the HYPROP. You'll see a little bit of discrepancy between the HYPROP and the WP4C, and that's mostly due to the fact that that's in the 0 to negative 100 kPa range, where the WP4C is not always going to be 100% accurate. But within the sample, we also used intact samples that you saw from some of the images earlier. That we used those intact samples to take to run in the WP4C and make those measurements using a drying technique. So we saturated all of the samples and then let them dry down and dried them down at different rates. So this is one sample showing what you can do with these two instruments together. So in summary, there are many tools available when you're wanting to measure water potential in soils, and you have to consider what your goals are, what range are you working in, what are you wanting to, what are you trying to measure, how are you wanting to do this, are you in the lab or in the field, and again, what's your price range. The HYPROP and the WP4C are a good option when trying to measure and generate the full moisture characteristic curve in the lab. But of course, with these two instruments, it does require some skill and technique and some practice. It takes a little bit of time to get good at using these two instruments together. But it can be done, and you can generate some really nice data using them. And as with any tool for measuring soil water potential, again, there's a bit of skill required to use the instrumentation to its full potential. For further conversation on this topic, please visit the soil water potential section of our forums and leave some discussion points. And we'd love to chat about this and see what you guys are doing out there and see if we can learn from you, if you can learn from us. So we always love to discuss these things. So please visit our forum section and leave some questions or some topics, and we'll go further into them. So now we'll go on into questions.